All right, welcome back. Diagonalization. Yes. It is as awesome as you've been thinking it is. All right, would be. Ooh, let's not go there first. Okay, diagonalization. We have seen a couple of factorizations of A, right? So it took us a long time to get to LU decomposition, very useful. QR, again, very useful thing. But now we're going to get a whole bunch up here. And the first one is diagonalization. So, important thing here, we're going to assume that n has n linearly independent eigenvectors. And we know that's always true if A has n distinct eigenvalues, right? None of them repeated. We'll see some more things soon for symmetric matrices. Okay, so we're going to assume that's true. So, which means that they form a basis for Rn. And that means if we stack them, right, we put them together like this in a matrix, eigenvector 1, 2, up to n, we'd have a nice matrix that's invertible, right? Because of all of these good things we know about. They're linearly independent. It means there's no, the null space problem would be just 0. The only way to combine them is 0 of each one. Okay. All right. But let's sort of build a little story here. So we know this, right? So we know we have these. We have, yeah, let me write this. Okay, so we know we have this, a basic thing, and it's going to be true for I equals 1 to n. And it could be that the lambdas are repeated. I was just giving you another example. So we have these n equations. The monks appear, and they suggest we try some things, right? So we're going to create this matrix that I was just alluding to. We're going to stack the eigenvectors here. Yes, like this. And we'll call it S for no good reason. Just because monks said call it S. All right. We have to do what they say. They seem like good people. I mean, I realize they're just standing there, but so that probably doesn't sound like I'm telling you the right thing. Okay, so A times S. Okay. We know some matrix foo, right? So we know that if we multiply a matrix times another matrix, that this is the same as doing a matrix times the first column here. A times V1. Right? And let's be clear about what that is. This is a vector, right? This is m by n, and this is m by 1. So this is m by 1. This is matrix foo. Right? Advanced matrix wrangling from early on. Yes. And then the next one would be, this is just terrific, the next one would be V2. Good. And then we'd have a stack of them next to each other, and then the Vn one. Okay? Why did we do that? Well, monks told us to do it, but now we can see something very nice. The each A times V1 can be replaced by the eigenvalue story, right? So this is now going to be lambda 1, V1, really great, lambda 2, V2. So exciting. All right. This really is very beautiful. It's tragically, you can't do this for every matrix, every square matrix, because some of them don't have enough eigenvectors. Let's just have a moment for them. Okay. All right. And there's some madness. Jordan helps out again, but we're not doing that in this course. Right. We will diagonalize it as best as we can. We'll get to that. Sorry, we won't get to that. We will just get to pure, beautiful diagonalization. Okay, so that's pretty good. So now we're just back to sort of a simple thing. We have eigenvectors. And if we think about this for a while, with just a, right, these are just, right, just a number multiplying a vector. Yeah. So let's, again, there are monks whispering things. They're obsessed with baseball for a while, so they seem to have stopped talking about that. Cubs fans. Okay, so as far as I can tell, they may have been the ones who orchestrated the curse. Anyway, all right, so look at this goodness. So we can actually then extrude more sneakiness, right? So lots of sneakiness here. Ooh, sneaky. Yes. Right. If we look at this, this is right. So this column here, multiplying. You can see that's a column picture story, right? So there's going to be lambda 1, all these zeros below it here. It's only going to give us lambda 1 times v1, and that goes here. There'll be a lambda 2 here with zeros everywhere. That just picks out this one and puts it here. Very nice. So we've done something very sneaky. We've gone from AS to S lambda. So this is now, so this is capital lambda, right? The Greeks are involved again. Capital lambda. We're trying to do the best we can. We have lambdas all over the place, but it's capital lambda. Gets the it's a matrix. It's n by n, right? So these are n by n, n by n, n by n, and this is a beautiful story. Okay, let's do it. So we're going to assume A is a good matrix. It has its eigenvectors, right? That's the story here. It's a good matrix. Same this piece over here that has all its eigenvectors. So it means this too, right? Eigenvectors. So let's do that. Form a basis for Rn, and that is the same as saying this is true. That if we stack them all up, we can find their inverse. We know inverses take a bit of effort, but we're going to get to something even better soon. So the equation we just got to, AS equals S lambda, we could post-multiply, let's write this in, post-multiply by S to the minus 1, the inverse, right? And then S to the minus 1 is just A, right? So it cleans that off, yeah? And we end up with this story here on the right. Really fantastic. Ah, yes. Right? Normally there's lots of balloons and things. But, you know, budget. All right, so, okay, this is pretty fantastic. Amazing factorization. So it's different to things we've had before. It's actually, so this is called a similarity transformation. Right, this is a similarity transformation up here. If you can connect two matrices with this kind of structure with an S and an S to the minus 1, right? So an inverse like that, then we said that they're similar. Again, it's a more general thing, but we're interested in the fact that this is connecting A to a diagonal matrix, right? So here's the statement. We would say these two are, let's push the wrong thing. We say they're similar, right? A and lambda are similar. Right, so now this is pretty great. It's only for n by n's, that's true. It's only for n by n's. I'm going to have more soon on how this works, but here's a big idea, right? So that A times X, it's missing its hat. Got too excited, lost its hat. A times X, we're going to replace it with this factorization. And let me sort of just step through this. What we're going to see is that this piece, right, that's inverse of S times X, just changes the basis. You can think of it as not changing X, right? X is some point in space, it's some vector. We change from the normal standard axis to a new basis, the eigenvector basis. It's still the same vector. We're just going to represent it differently. We'll repeat this as we go along. Then we do the work, right? The diagonalization of A, that's the thing that will do the work, right? It will stretch whatever's in some eigenvector directions, maybe shrink over here, stretch. If there's rotation, it will do that too. And then this S here undoes the basis transformation, brings us back to the natural basis. So you can think of the S as not actually moving x at all, right? They just change the way we represent it. We do the work. The work is very simple to do when we have a diagonal matrix, and then we change a representation back. And so why don't we always just live in the basis of a matrix? Well, we have many different matrices. We need a standard way of representing everything. That's how we've built the whole story. Right? If we're in calculus, it might be I hat, j hat, k hat. We have a structure, and then there just are things that are oriented in different ways. That doesn't mean that but what it means is we can go to those representations, do the work, come back to our standard one, go to a different representation for a different matrix, and come back. All right, so that's huge, right? So, and here's a kind of a really big piece. You can think in a way, right? If A is diagonalizable, then A is really a diagonal matrix. It's actually really a diagonal matrix in terms of how it functions in multiplication. Right? As long as we look at it in the right way, as long as we represent things in the right way. So that is pretty spectacular. It gets us through this piece. Okay, so we're going to work on an example and then see how it functions. Yeah, and there are going to be two parts to this. All right, so let's go. So again, this 1, 1, half matrix that we know so well, these are our pieces. I'm just going to point out here that these are choices, right? So these eigenvectors that we choose, right? We could have any multiple, right? Any multiple would work. We want to make so, right? So any multiple, they're basis vectors for the eigenspace. These are pretty good ones. The unit vector versions would be nice too, and we'll come back to that later on. All right, so again, just note symmetry, right, which is hiding something special for us, or, well, we'll get to it. Okay, so let's just do this, let's just write this story out, right? So we just make S, we just line up the eigenvectors. Boom, boom. Then we compute the inverse, right? And so here's the inverse for a 2 by 2. You can remember that formula. So the determinant is here. You know about determinants. This is the determinant of S. Let me get it in here. So this determinant of S, it's a sad little s, S equals 2. And we've swapped, right? We've put some minus signs here and here, and we've swapped these two, which leaves it very similar looking. Okay, so lambda, capital lambda, very simple, right? Just the eigenvalues just lined up here, so it's 3 halves and a half. Right, we just stick them in here. And so we can put everything together. I see what I'm doing. Yeah, right. So here's S to the minus 1 is going to be here. 1, 1, minus 1, 1. There's a half. It is we can pull the half at the front this way if you like. But it's kind of nice to see where it is. I'm going to keep things attached to the right pieces. There's the what A really looks like. Let me fix this up too. That's an A. And then we have here S, which was S is, yeah, minus 1 on the top. So this is a better way to write A. It's just a better way to write A. All right. This looks fine. 1, a half, 1. But this shows us what A does in a clear way. Okay, good. So we're going to look at two examples. As I just said, this A times X piece, right? And A to the K, right? Given that we have this form here, now we've elucidated this. What am I doing? This is a much better version of this matrix. Now it's 3 matrices. It's true. It's 3 matrices, but we can see their jobs, right? And this is something we're going to do more and more with the singular value decomposition is a similar kind of game, right? We break it into these 3 pieces that each have good reasons for being. So let's just take an example here. We're going to take x equals we're going to add the 2 times each eigenvector together. And in fact, I better be careful there. I don't want, yeah, that should be this and this. We're going to do unit vectors later on. All right, good. So let's just add them together and we'll multiply a times x in 3 different ways, right? So 3 ways in 3, so a times x in 3 ways. Right, so let's just get x. We're just adding these 2 eigenvectors together. Right, so there's 1, 1 and minus 1, 1, just 2 times each one. We add them together, we get a 0 here and a 4 here. Good. So we can simply do a times x. Take our 0, 4, just multiply it by a. Fine. And if we do that, right, this is just standard multiplication, we get a 2, 4. But we've just crunched it, right? There's no great understanding here. Right. Now, if we knew, and of course we did, we set this up. If we know that it's the sum of 2 eigenvectors, right, with these weights on them. Yep. So if we do that, then it's easy, right? A times 1, 1 is just 3 halves times 1, 1, and a times minus 1, 1 is just, that is minus 1, 1 times a half. Right, it's simple. We don't have to do the multiplication once we know the eigenvectors. If you add everything up, we get the same answer, right, as before. Right, fine. So that's better. Now, breaking that up, breaking a vector into 2 eigenvectors, right, we don't know this, right? We may not, maybe if I can say this, you know, may not know this. But we do because we set it up. So if we don't know that, then this is the way we would do it. We just replace a with s lambda s to the minus 1. And then let's work through and see what it does. So here's s to the minus 1 here, right? Multiplying 0, 4, that's our original thing. So what happens? So we just multiply it. We end up with, there's a 4 and a 4 divided by 2. So we end up with 2, 2. This is 2, 2, right? That is actually, this is the representation of x in eigenvector basis. It is 2, 2. It's, right? It's 2 of v1 and 2 of v2. So that 2, 2 exactly means that. So let's keep going. The lambda comes through, so it's diagonal multiplication, a diagonal matrix multiplying, very simple. 3 halves times 2, a half times 2, so we end up with 3 and 1, right? So very, very simple. And then we have s, and s is going to undo things. So this is still in, and this is in eigenvector basis still. Right? We've done the stretching, and now we have to go back. So this is return to natural basis. Natural basis. Use those interchangeably, right? 2, 4, as before. So very good to understand these 3 ways, right? So one is just the calculation. The other is, well, let's say we actually know the representation of this vector. We don't usually, we want to let the diagonalization do that work for us. And we see that's exactly what it did. It turned it back to 2, 2. It took 0, 4 and turned it into 2, 2. That's what s to the minus 1 did. It changed the basis. All right, so let's look at this picture here. So first of all, this is, if I got this right, yeah, this is the original vector. That's x, right? It's 2 times v1 plus 2 times v2. Okay, good. A times x is over here. This is our final, right? This is all in our natural basis. right? 2, 4. But here's the eigenvector basis, right? 1, 1 and minus 1, 1. And if we, right, so if we're in that basis, this vector is just going along, they're both just going along the axes, and we simply halve one of them and multiply 1 by 3 halves, 50% longer. So this one shrinks, right? So we shrink, so we go from here to here, and we go from here to here. And then we add them together, and then we go back to our original basis. All right, so this is a very important thing to understand. Hopefully that is a good start to it. We're going to come back to transformations in a little bit. All right, so a to the power of k. Look at this, great. So a squared. Actually, this works for negative powers too. And of course, this is all if we can have inverses, which is all about whether we have a linearly independent set of eigenvectors, basis. Right. So let's do these two things. This is, right, so this is a squared, we're just multiplying a times a. We have these two pieces together. This is a cubed, right? S minus 1 times inverse times this guy. Same with this one. There's an identity here, identity here. So identity times the adjacent matrix, we can just replace it. So let me put this maybe here. Right, so the whole thing is equal to, in this case, this is S lambda squared S minus 1. So that is fantastic, right? Super easy to do. So if you want A and the same thing happens here, these parts collapse, right? Essentially they just get absorbed and we'll get the same kind of story. So this will be, again, S and then lambda cubed S minus 1. So this is pretty fantastic. And so in general, we have a lambda matrix in the middle to the power of k, and that is very, that's a very powerful story, right? I mean, this is fantastic, right? So now, because we can compute this very, very simply. Easy. This is easy. We've done some work, of course, to get the, that's close enough, to get the, We've done a lot of work. This is super easy. And then we just have to multiply by s and s to the minus 1 to find the power of k. Right? I've said it twice. Super easy to compute. Again, all right, because capital lambda to the power of k is just this beast here. We just have to raise the individual eigenvalues to lambda. So what we'll see, so very important, so clearly important, is whether the magnitude of lambda is, if lambda, let's say I is less than 1, lambda I equals 1, and lambda I is greater than 1, right? You can see if the magnitude is less than 1, then it will disappear. Right? As k gets large, the entry in here will disappear. If it's equal to 1, it just stays there. And if it's greater than 1, it grows and grows and grows. So the largest eigenvalue will dominate. We can see, right, we can see that largest eigenvalue and the eigenvector associated with it will dominate. And it could be repeated, lambda to the k, and therefore a to the power of k. Right, so this is a very important thing. The largest eigenvalue is a big deal. It's a big deal by magnitude. So here's an example. All right, we're going to take our matrix to the power of 523. Craziness. That would take a while. I mean, you could stick it into MATLAB and so on, but certainly if you wanted to compute it yourself by pencil, that would be bad, and you wouldn't have any understanding of why it did what it did. So here's S, usual thing, right? So here's S. Here's S to the minus 1, and this is lambda to the power of 523. So you see what's going to happen. This piece is going to go to 0, right? So half to the power of, right, blows up. And so it's approximately, right? Approximately, if you multiply this thing through, 1, 1, 1, 1. So that eigenvector is repeated, if you like. And this is just huge, right? So it's growing and growing and growing. So, but that's, we've computed it pretty easily. I mean, we've had to do some work, if you like, offline. Now we can compute any power of a matrix. So a couple of nice little extra pieces here just to finish. This makes sense, right? So a to the power of 0, so lambda to the power of 0 is really just the identity. So this would all collapse, right? So that makes sense. It's like, 2 to the power of 0 equals 1. The inverse works as well, yeah? So this is a to the minus 1, so we're putting the power here and here. That's good too. So these things again, this is the identity, and then these two give us the identity as well. Inverse of lambda times lambda. Right, so if this was, let me see what these are. This is a to the minus 1, and this is a equals the identity, right? Because eventually we get this one as well. Let me get this right. I want to add, they all match up with each other. Identity, 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 right? So this is really a to the minus 1, and this is a equals identity. All right, so the whole thing generalizes. So you could have, if you want, you could, this makes sense too, right? A to the power of a half equals s lambda to the power of a half s to the minus 1. That's cool too. Let me get this right. So I'm going to move that a little bit. That's pretty nuts, right? Works too. So if you multiply these together, a to the half times a to the half, right, it will equal a to the 1, right? So now we can have arbitrary powers of matrices. Pretty bananas. All right. That is a cool thing. I'll set up the Fibonacci example in the next little piece. It's a great thing to work through yourself. Many years ago, it was one of 4 questions and pretty much half of the 3-hour exam that I did for linear algebra back at the University of Melbourne. It's a long time ago. But a great joy to work through that problem, right? We get the golden ratio, lots of other good things. But nutshell for this is diagonalization is amazing. The monks suggested this craziness, and it's really all here, right? This fantastic thing. We're going to have more in a second in a couple of episodes from now, but this is pretty amazing. You have to have n linearly independent eigenvectors. We know that is always true if the eigenvalues are distinct. It's certainly true for cases where they're not distinct as well, but it's something we have to worry about. But once that's there, we can do all sorts of things, raise powers. We can understand more deeply how a times x works. Again, more of that soon. We could raise it to arbitrary powers and indeed even to non-integer powers. Okay, you should be psyched. You should be thrilled that this is all true. It is.